Okay, so I needed to show you an approach that you could use that we hadn't discussed in class, but will save you quite a bit of time on the exam. And that is, let me remind you that we know from our experimentation that the acceleration of an object is directly proportional to the net force acting on it and inversely proportional to its mass, which of course is more familiar in the format of net force equals mass times acceleration. And you'll recall that before we took that statement and we broke down acceleration into its definition, which is the change of velocity over time. And then we multiplied both sides by time to get this expression, which we mentioned that the left side is what we call impulse, and the right side is what we call the change in momentum. And so this was just another way of phrasing a Newton's second law, talking about how an impulse on an object can change its momentum. And that can be helpful when we look at a graph. As you're familiar with the other graphs that we've done so far this year, if you have one value on the y-axis and the other on the x-axis, then the slope can tell you the change in y over the change in x, and that's often physically meaningful for us. For example, when we're taking the position versus time graph and we get the slope as the velocity, or the velocity versus time graph and the slope is the acceleration. But in this case, we're not interested in force over time, but rather force times time. And as you recall, if you take y times x, then that's the area under the curve. And we saw this in the format of when we had acceleration versus time, we took the area bound by that curve, it gave us the change in velocity. And similarly, the velocity versus time graph, when you took the area bound by that curve, it gave you the change in position or the displacement. And so we're going to use that to solve a problem that would, using kinematics approach, would take us a lot longer. But let me show you both. So for example, let's say this is the graph of a net force acting on an object as a function of time. And I know I missed the 3 there, but just pretend that it ends at 3. Say we have the question that given this force versus time graph, if that acted on a mass of 2 kilograms and that object started at rest, how fast would it be going at 3 seconds? And so again, there's 2 approaches. You can take a kinematics approach where you would simply break it into 2 sections, because we have obviously a graph that changes functions. And the first section, we could talk about the average acceleration, and we'd find that by looking at the value of the net force, which is 4, and dividing it by the mass of the object, which is 2. So during those first 2 seconds, there's an average acceleration of 2 meters per second squared. And so since it started at rest, we can apply our kinematics equation to find out that it's going 4 meters per second after that first 2 seconds. And then we'd have to look at the second section, where the force changed from 4 to 0. And from there, we could find that the average acceleration is the average net force, which going from 4 to 0 constantly at a constant rate gives you an average of 2, mass of 2 kilograms, and therefore an average acceleration of 1 meter per second squared. Incidentally, notice this is going to come up on Tuesday. Is that a negative acceleration or a positive acceleration? Well, it's a positive acceleration because the net force is positive. Again, be careful. With every graph that you have, be careful. Am I asking for the instantaneous value on the graph? Am I asking for the slope? Or am I asking for the area bound by the curve? And in this case, since I'm looking for acceleration, I know that the net force is positive 2 at 2.5 seconds, and therefore the acceleration at 2.5 seconds is that positive 2 divided by the mass 2, or 1 meter per second squared. So I take that acceleration for that 1 second, and I use my kinematics equation again, and I say that the final velocity then is equal to the initial velocity plus the acceleration times time, which in this case is going 4 at 2 seconds, because we saw that it sped up to 4 in the first 2 seconds. and then the acceleration of 1 for 1 second will take it to a final velocity of 5 meters per second after that 3 seconds. So that's one approach. You can see it's a little clunky and a little time consuming, but look at this. We can graph as well. If we use Newton's second law and the definition in terms of impulse and momentum, then the left side of that equation, F times t, is the area bound by the curve of our graph. And so if we were to calculate the area bound by this curve, then we wouldn't have to break it up into 2 steps, and we can do it a lot faster. We can take the area of that entire graph. You've got a rectangle that's 4 by 2. You've got a triangle that's 4 by 1. For areas of 8 and 2 respectively, for a total area of 10. And that's the left side. So that impulse causes a change in momentum, and that impulse is 10 and the mass is 2, and so the change in velocity for the whole time must be 5 meters per second. And of course we would expect it to, and it does agree with the answer that we got when we did kinematics. So once again, fairly straightforward, a lot faster than the kinematics approach, and can save you some time on the exam. But again, just be careful. Always look at what kind of graph that you're looking at, what can be determined from that graph, and what then am I asking about? Am I asking about the instantaneous value? Am I asking about the slope, or am I asking about the area bound by the curve? All right, let me know if you have questions. Thanks.